Welcome to Lesson 2F, Rate of Rotation and Vorticity. In this lesson, we'll define the rate of rotation and a related property called vorticity, and we'll compare two circular flows. First, a quick review of the rates of fluid motion. In the previous lesson, we defined rate of translation, dilatation, and shear strain. Now we're going to discuss the rate of rotation. We all know what rotation means, when a fluid particle rotates about some axis. But we need to extend this to 3 dimensions. To do so, we look at the same diagram we had in the previous lesson, which shows general motion and distortion of two initially perpendicular line segments, PA and PB, at time t, move and rotate at some time t plus dt. And we called these line segments now P', A', and P', B'. We define this angle as d alpha, but it's a negative change of angle since we calculate angles mathematically positive in the counterclockwise direction. We call this angle d beta, which is positive. Rate of rotation about the x3 axis is defined as the average rate of rotation of two originally perpendicular line segments in the x1, x2 plane. Well, that's exactly what we have here, two initially perpendicular line segments, and so we simply averaged angles d beta and d alpha to get the rate of rotation. Mathematically, the rate of rotation about the 3 axis, in other words, mathematically positive or counterclockwise, about the x3 axis. So this rate of rotation about the x3 axis ends up being the average of the rate of change of d alpha and d beta. However, since d alpha is negative, we write 1/2 d beta dt minus d alpha dt. After some trig and algebra, the rate of rotation about the x3 axis turns out to be 1/2 del u2 del x1 minus del u1 del x2. This is component 3 of the angular velocity vector. In common notation, we write this as 1/2 u2, 1 minus u1, 2. Similarly, about the x1 axis, we get 1/2 u3, 2 minus u2, 3. And about the x2 axis, we have 1, 3 and 3, 1. These are the components of the angular velocity vector, although not in the normal order of 1, 2, and 3, since we derived this one first. Let's summarize all 4 of the rates of fluid motion. Rate of translation ends up being simply ui, the velocity vector. The rate of dilatation, or the linear strain rate, has these 3 components, which turn out to be u1, 1, 2, 2, and 3, 3. The rate of shear strain, or shear strain rate, has 6 components and are summarized here. And remember, last time we combined these two into one strain rate tensor, but we had to multiply a factor of half on these shear strain rates, the off-diagonal terms, to get our strain rate tensor. Now we just looked at rate of rotation, and we had these 3 quantities. As I said, these 3 are the components of the angular velocity vector. But in fluid mechanics, we typically talk about vorticity instead, which is twice the angular velocity vector. In this course, we'll use omega, which is a vector, or omega I in tensor notation, although some authors use Greek letter zeta, for example in my undergraduate fluid mechanics book. The third component of the angular velocity vector is 1/2 of u2, minus u1, When we multiply by 2, the x3 component of omega, the vorticity vector, is simply u2, 1 minus u1, 2, without the factor of 1/2. And similarly for these other 2. The reason we like to use vorticity is that it's also defined as the curl of the velocity vector, which is useful later on. In tensor notation, we write this as omega k is epsilon ijk del uj del xi, or in common notation, epsilon ijk uj, I. Vorticity will be a very useful property in studying fluid flow. Now let's compare 2 circular flows. The first one is solid body rotation. Let's look at the x1, x2 plane with the rotation coming out of the plane. In other words, counterclockwise rotation, which is mathematically positive. We're going to use cylindrical coordinates r and theta, or r theta z coordinates, and we'll let omega naught be the angular velocity, in this case coming straight out of the page. The streamlines of the flow will be circular and concentric about the origin. Since it's solid body rotation, u theta increases linearly with radius and is equal to omega naught times r. ur and uz are 0 in this solid body rotation flow. Let's calculate the vorticity for this flow. Again, omega is the curl of the velocity vector. In cylindrical coordinates, we look up the components. Omega r is 1 over r del u z del theta minus del u theta del z, while uz is 0 and u theta is not a function of z. So this term is 0. Omega theta turns out to be del ur del z minus del uz del r, both of which are 0, as we said here. Omega z is 1 over r del r of ru theta minus 1 over r del ur del theta. Again, ur is 0, but this term needs to be analyzed. By the way, you can look up these components in cylindrical coordinates in any fluid mechanics book, typically in the appendix. This is 1 over r del r of r times r omega naught, since u theta is omega naught r. We differentiate and simplify and get 2 omega naught. Thus the vector omega, the vorticity vector, has only one component and it's in the z direction. Again, this is in the r theta z coordinate system, and that non-zero component is twice the angular velocity. So here omega is twice the angular velocity vector, which is what we already stated previously. So this answer agrees with our previous statement. The second circular flow is called a line vortex. Again, in the x1, x2 plane, the line vortex will have circular streamlines. So the streamlines look similar to the solid body rotation case, but the flow is quite different. If I sketch u theta, it's infinite at the origin and asymptotes to 0 at infinity. Again, in r theta z coordinates, there's no radial flow, but u theta is some constant over r, and uz is 0. Again, let's calculate the vorticity. We'll find that omega r and omega theta are 0 as previously, since ur and uz are 0 and theta is only a function of r. In fact, this flow is the same except we had a constant times r for the solid body rotation, but a constant divided by r for the line vortex. What about omega z? Using our equation from previously, we plug in u theta and the r's cancel, so we get 1 over r del r of a constant. But the derivative of a constant is 0, so omega z is 0 over r, which is 0 everywhere except at r equals 0, the origin. So the three components of omega are 0, 0, 0, except at r equals 0, where omega z is infinite because of this r in the denominator. In other words, vorticity is concentrated along the z-axis. This leads us to the concept of rotationality. Consider again our two flows. For solid body rotation, omega was not 0. This flow is what we call rotational. For the line vortex, omega was 0, so we say that this flow is irrotational. However, we have a singularity at the origin in the x1, x2 plane. Let's ignore this singularity for now and look at the rest of the flow. Rotationality means that individual fluid particles rotate in a rotational region of flow, and fluid particles do not rotate in an irrotational region of flow. This is our definition of rotationality. And since vorticity is twice the angular velocity, we can tell by omega, the vorticity, whether the flow is rotational or irrotational. I illustrate these two flows with fluid particles that are smiley faces. If we start here, we see that the smiley face, in other words the fluid particle, actually rotates once every time the flow goes around. This is solid body rotation. For the line vortex, however, starting at the same location, we see that as this particle moves around, the orientation does not change. This is like a merry-go-round, and this is like a Ferris wheel. In a merry-go-round, all the people rotate as they move around in a circle. In a Ferris wheel, the cars stay vertical as they move around, otherwise people would fall out. I'll have two of my students, Duck and Dick Dynamics, illustrate this with some visual aids created by two former students. Okay, Duck and Dick, we're ready to roll. Turn your wheels around. Now start rotating them. What do you observe, Duck? As I rotate, the arrows rotate right with the wheel. What about you, Dick? As I rotate the wheel, these arrows stay straight up. They don't rotate at all. I guess that's why they call it irrotational. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.